Hi, welcome to question 9 of the 2023 paper 1 for the Leaving Cert Ordinary Level. If you want a copy of this set of notes I'm working off, just send me an email at shanetroy@gmail.com and like and subscribe to get access to more playlists. So question 9 is one of the questions in section B, and they can be fairly long and tedious, but we'll get stuck in. So part A here is worth 10 marks across a B scale, so there's a big jump for the any correct relevant steps. Let's try to get that. The diagram below shows the actual daily number of new cases of a disease. So I wouldn't have mentioned disease for a few years in 2023, but that's not my decision. From day t is equal to 0, so from day 0 to day 25. It also shows the number of cases according to a mathematical model over the period of time. So you have the actual number of cases dotted along here. So there's a trend that's increasing. Now it's not linear, okay? It's curved, so it could be maybe quadratic, could be starting exponential. And then you have the what the model says the case numbers will be, and that's ultimately why we do mathematical modeling. We don't know the future, so with data, hopefully, if the data and the model are correct, we can see into the future. So if you're at day 10 and it's following a recognized pattern for that disease, you know what your case numbers will likely be, and then you can plan for it. Okay, so we know the trend's going up. Okay, from the diagram, estimate the number of actual new cases there were on day 12, using the relevant dot. Now they're saying that for a reason, but let's find day 12. Now they don't give you a scaling. Okay, so that was a day 10, 11, 12, 13, 14, 15. So this is day 12, and estimate the number of cases. Now I have it on the next page. I'm trying to bring a line over. We're talking somewhere around here, which is, depending on your perspective, either 1400 or 1500. So the answer I have is 1400. Now, I noted that on the marking scheme, they said 1500, but that was just their estimate. The tolerance for that from the marking scheme was between 1300 and 1700. So a fairly wide margin, because again, perspective matters. Right, that's part A, part 1. So part A, part 2 is only a 5B. It says, according to the model, the curve, there were 1,000 new cases on day t is equal to 12. Okay, so we have, now I said 1400. Okay, take away 1,000. That means there's a 400 difference. 400. Let's put the word difference. Okay, excuse my bad writing. Right away there, I have the 3. That's the correct relevant step, clear as day. Now, percentage error, okay, I have it done on the next page. I always forget that formula. I have a mental block for it. It's the actual result, take away the estimate over the actual. Okay, so the actual result was 1400, take away the estimate was 1,000. Because the model is estimating, okay. And then divide by the actual, which is, this calculation doesn't seem right. Okay, I just realized I had an error there, so I just paused and fixed it. I should have had the actual being 1400 on the bottom. So once I do that calculation, it's 1400 take away 1,000 is 400. Okay, divided by the 1400 on the bottom to get a percentage multiplying by 100. And I got 28.57, which rounded up to 29%. Now the marking scheme says 3,300, but that was based on their reading of 1,500. Okay, so that was any answer from part 1 we accept as correct in part 2. So, okay, apologies for that. Now, part 3 then says, show that it takes approximately 5 days for the daily number of cases to double, according to the model. Okay, so we have the model here. I have the answer. I just took a 5-day period, so from 15 as far as 20. Okay, now I'm reading that as being from here, so I'm reading that as 3,100, and here I'm reading that as 1,500. Okay, so day 15 is, I probably should have been more explicit. No, the marking scheme is no less explicit. Day 15 is 1,500. Day 20 is 3,100. That is double. Therefore, now I could have said 3,100. Okay, is almost equal to 2 times 1500, therefore double. Just if I want to be really explicit, although the marking scheme doesn't call for that. That is only a 5 marker. So any, like, I mean, if you took any point on it, especially as it starts to speed up here, you definitely in the 5-day period, maybe less so over here. Okay. You might have had a different answer. Although I'd have to look at the numbers, like if that was, yeah, no, it doesn't look like it over that 5-day period. Now, part 4 says, hence estimate on what day, the value of t, the number of new cases will first be at least 100,000. Okay, now this is actually a weird thing because you don't have any data. But if we assume the model is going to hold, okay, when will that doubling get over 100,000? So on day 20, I estimated 3,100. So if it doubles, it'll be 6,200 on day 25. It'll double to 12,400 on day 30, double again, day 35, double again, day 40, double again on day 45. Okay. Now, why does that seem wrong to me? Okay, the mistake there is this 4,900 should not say that. I'll fix it after. That should be 96,000. Okay, so the next day, it will likely have risen above 100,000. So day 46. Okay. So apologies for that mistake. I'm just looking at the markings to make sure I'm not making any more mistakes. Their estimate is slightly different. In fact, my estimate here of 96,000 would be slightly higher because they were using the, and I'll show you what I'm talking about just directly. That's the marking scheme right there. They just give the days, and they start off at 1,500, whereas I started off with 3,100. So, and I had the error there. So that's cool. Part 4, then part, 9, part B, part 1. Now we have a scientific notation here. This is diseases again. We're really going for it. The daily number of new cases of a different disease can be modeled using this function. Now this looks exponential to me, okay, and it's using function notation. So remember, this d of t is the same thing as d with a lowercase t. It's not that they're multiplied. This is just a descriptor for the function as such. And then it's got this weird shape. It was not quadratic. Okay, it'll be exponential. And part 1 there says, fill in the table below to show the values of d of t for the given values of t. So if you test this one here, if you put 2 in to this function, okay, in fact, I'll just show it. Then I have 2,100 times 1.18 to the power of 2. Now that should equal to, in decimal, 2,924, and they've rounded it down to the nearest whole number, so 2,924. So if you do the same thing for 0, okay, now that one should be 2,100 because anything to the power of 0 is 1. 2,100 by 1 is 2,100. Do it for power of 1. You've done the power of 2, 3, 4, whatever ones are left. Okay, show a sample calculation and you'll be good to go. Okay, it's a lot of marks. That is a chunk of marks across the Leaving Cert for what is like a fairly straightforward question. It is putting up, I'm assuming, putting people off because the function notation, but also like the power. Okay, and people may not know what to do, but fall back on the normal strategies. If you're substituting something in, do it in brackets, put it to the calculator, write down the answer. That will get you through. Now, 9 part B, part 2, you're asked to graph them. So look, if I was being very straightforward, at T0, at 2,100 is probably somewhere over here. Okay. Then the next one where T is 1, 2,478, it's a little bit below here. It's probably something down there. Now, I'm not going to bother messing on the screen. If you're close enough, okay, just don't be too loose and make sure you make a good clear mark. You'll end up with a trend like this, okay, and that's that question. Now, part B1 and 2 are marked together, so it's not 20 marks for each part, okay. Now, part B, part 3, oh, the words. Measures are put in place to slow down the spread of the disease. From t is equal to 14 day onwards, the number of new daily cases starts to decrease. So whatever's happened to the trend, okay, so it was going up. If it was no intervention, it would have went up, but now there's intervention, so it's slowed down, okay, and at a certain point, the numbers start decreasing. So you end up with a different shape completely. There's a different model describing after day 14, and that's this model here. Now on t equals 14 days, there are that many cases. According to the model, work out the value of a. So if I write out my function, so k of t is equal to a times 0.83 to the power of t. Now, I know t, okay, that's 14. I know k of t. So when t goes in, okay, it gives an output, and that output is 21309. What I don't know is the value of a, so I'm going to have to use algebra. So there's my substitutions. Okay, my 21300 is the k of t, the a times 0.83 to the power of 14. Now it's pretty simple. Okay, if I want to get rid of something that's multiplied, divide it by that thing, even if it's a really awkward looking number, which this is. Just divide it by it. Okay, you don't need to worry. You're not going to have to deal with it. You're going to have to just recognize that's what's happening. If I do it one side, I'm going to have to do the same thing to everything on the far side. Now, on this right-hand side, these things cancel out. So they're gone and you're left with A. On the far side, that can be programmed in the calculator. Now, it'd be awkward because there's a power on the bottom, but put it through and whatever answer you get, even if it's wrong, you have the correct work shown on the page. I got this number, 289,380.8421. And they say they want that written in the form of b times 10 to the power of n, where b must be between 1 and 10. N is an element of n. That means your n is a natural number. It's a positive whole number, so don't worry about it. And b is corrected 2 decimal places. So at the minute, that 289, the decimal place is all the way back here. They want it moved so that this number is between 1 and 10. So I'm going to move it once, twice, 3 times, 4 times, 5 times. Now, that number is 2.89380841 by 10 to the 5. 10 to the 5 is 100,000. So you're basically just dividing by 100,000 and almost writing down what you did in reverse. And that makes a different number that's more easy to manage when you're doing calculations. And then they say they don't want all these decimals at the end. They just want 2 of them. So all of these go away, but the only one that matters is the 3. 3 is less than 5. The 9 stays the same. Now, scientific notation is weird, but all you're really doing is moving the decimal place. And if you move it to the left, you're multiplying by 10 to the power of whatever times you move it. So I moved it 5 times, so I multiply by 10 to the 5. If I'd moved it twice, I would have multiplied by 10 to the 2. Okay. So I get it. I've often struggled with scientific notation, but once you get the handle on it, it actually becomes fairly straightforward. But again, like all things, that's the case. Now, question 9 is finished, thank God. That took forever. If you want to copy the notes I'm working off, email shanetroy@gmail.com and like and subscribe to get access to more playlists. Thanks.